Okay, so thank you for the invitation. And today I want to talk to you about the understanding of the impact of hydrogen bonding on the polymerization of monofunctional vinyl cyclopropanes. But before starting with the science, I want to talk a little bit about myself. So I'm a PhD student at the University of Bayreuth, which is located here in southern Germany in Bavaria. And this is our campus, which I think is a very nice one because it's very green, very natural. And there I work in the Department of Macromolecular Chemistry II under the supervision of Professor Agarwal, and we are located here in this building. So most of you probably already had the problem that when once or another time you needed to go to the dentist because you had a broken tooth or a hole in your tooth. And I want to start to talk about different dental materials and their pros and cons here. First is amalgam, which is a very long known material, and it's used very much because it's quite cheap and it has very nice properties. It's mainly used in the back of your mouth, in the back tooth, because of its negative aesthetic effect, as you can see here on the picture. And when I picture my parents, I always see in their mouth, and they talk to me, where their teeth were damaged, so it's not the nicest way to repair this. Also, it contains mercury, only in small amounts, but still. And for people with a metal allergy, this is not suitable. There is a second material, so we can use precious materials there, which are also have very nice properties and have a more universal use. But there the drawback is that they are very costly and also the negative aesthetic picture. I mean, for some it might be positive, but I think at least that when you see where the tooth is damaged, that's not so nice. The third one is ceramics, which also show nice properties, but are also very expensive. But at least they challenge the problem with the aesthetic look, so you cannot see the difference between the filling and your teeth anymore. But there is one other drawback, which is the long-lasting procedure, because it's very hard to work with, and it's actually a product which is stronger than your tooth, so if not done right, it might even damage the opposite part. And the last one is composites, which is a relatively new material, and it is increasing in its use. It also shows no aesthetic negative effects. You can basically tune the color for the teeth you want. And it's also very nice that you can not only fill your teeth, but also replace parts, as seen here in the picture. But there are also some drawbacks. One is that it's the weakest filling on the market, so you have to replace it every few years. And that the procedure is also quite long, and this is due to volume shrinkage. So these are dental monomer matrices which are used in this field, and they all combine here this methacrylate moiety, and that's actually where the problem is, because if you look at the polymerization, we have small molecules which are together on a certain distance, usually around 200 picometers. And then upon polymerization, there is a bond formed, which usually is shorter, and therefore the whole material is contracted. And when we look at the volume shrinkage, we see here for 112 DMA, for example, it shows a volume shrinkage of 11%, which is not so nice. And for materials which are better, like this bis GMA, there we have the problem that the viscosity is quite high. And we can reduce this viscosity by mixing a few monomers, but then the shrinkage increases. So the question is, what can we do to work against this and to improve the procedure here? And one answer would be to introduce additional bonds into the polymer backbone. And this can be done by ring opening polymerization. And here is a graph of all, or maybe not all, but many different cyclic monomers which are capable of ring opening polymerization. And there are a lot of them, of course, but These two are the mainly used in science, so ketene acetyls and vinyl cyclopropanes. And as you saw on my title slide already, I'm focusing here on the vinyl cyclopropanes. In early days, so quite some time ago, there was a polymerization, radical polymerization already reported of this VCPs, how they are called. This VCP-D ester, where we attack here in this vinyl bond, we open the ring and form a linear chain. But the problem is, as you can see here on the graph, that it's a very long reaction and the conversion is really not high. So after 20 hours, we have, it's not good to see, but roughly 20 to 30 degrees of conversion. We also looked at that in our group a few years ago, where we synthesized this bifunctional VCP ester, which is close to the commercial available materials. And we also saw here that after 30 minutes of irradiation, so it was a photopolymerization with light, we also only got a conversion of 35%, which of course is not what we want. So what to do here? My predecessor found another molecule by combining this VCP with a diamine to form a VCP amide. And as you can see here, very nice on the graph, now we have a polymerization which is much faster, and also the monomer conversion is really good. So we get almost a complete conversion after only a few minutes. Now, looking at the shrinkage here, we see that these kind of molecules are also in the range of the best ones on the market already, and they have the advantage that the viscosity is much lower here. And by combining these two, we could even decrease the viscosity by a lot without changing the shrinkage. So the concept between these VCPs is once that the low volume shrinkage is due to this ring opening mechanism I showed you here. It's a little more into detail. So we attack with a radical, and then we form either here the linear chain or via backbiting the cyclobutane ring. And this ratio is basically what distinguishes between how big the volume shrinkage will be in the end. One possible reason for this fast and complete conversion is that due to this amide here, we have the possibility of preorganization via hydrogen bonding. And this low viscosity is probably due to the sterical hindrance of these methyl groups. The problem with these bifunctional systems is that they are very difficult to investigate. And that's why in my work, I started working with monofunctional monomers to better understand this and to investigate this further. So this is the synthesis route, basically what I did. So first there is the forming of the VCP diester, which is then partly hydrolyzed to form this mono acid. And then in an esterification reaction, I could obtain various new monomers. So these are the side chains I used, which are then polymerized for the polymer. So I used 4 different side chains, and these 4, they all have different possibilities for preorganization. So we have the carbonate, which of course cannot form any hydrogen bond, so no preorganization. The urethane and the amide, there we have 1 hydrogen donor and 1 acceptor, so we should have a preorganization there. And the urea, here we have actually 2 donors and 1 acceptor. So one can postulate that the degree of preorganization would be highest for the urea, then followed by the urethane, because here we have this oxygen which can pull away some electrons, and therefore this bond should be a little stronger than for the amide, and then followed by the carbonate. The monomers were all characterized by NMR, IR, and mass. And for NMR, there was a 1H, 13C, and also a 2D experiments conducted. For this 2D bonds, one was the HSQC, where we see the coupling of the proton to the carbon where it's connected to. But this is not enough to really distinguish between the different signals. So also HMBC was conducted, where we can see also coupling to neighboring carbons there. Then, of course, I wanted to look at the hydrogen bonding, and this was done by a solid state NMR, because there we don't need any solvent and therefore can only look at the effects our molecule is showing. Here we started at room temperature and we raised the temperature up to 60 degrees, and every 10 Kelvin we conducted one measurement. And what we can nicely see is that here at 6 ppm we saw a shift in the signal, which is the here this NH proton towards a higher field, so the hydrogen bond is weakened there. And this we saw for all three monomers which are capable of hydrogen bonding. And also when we look now at a change in chemical shift, what we could observe is that monomer 2 and monomer 4 are having more or less the same slope here, while monomer 3 shows a much lower slope. But in contrast to the other one, here we have two different changes which correspond to the two different protons here. So then the photopolymerization was conducted. This was done with visible light and with an initiator. And here on the left, you see the conversion curve over time. And what you can see is that for monomer 3, we have a very high initial rate of conversion of polymerization, which is also seen here on the chart with 25% per minute. But then the polymerization fast gets to a plateau, and the overall conversion is not as good as, for example, for monomer 2 or 4, which are a little slower, but the overall conversion is with 97% almost a complete conversion. The question was here, why is this actually happening? So you would expect that the fastest polymerizing molecule should only also show a very good high conversion in the end, and therefore photorheology was measured. Here we have a monomer on a glass plate, and with a rotor with a constant shear rate, we rotate it to obtain the force needed. On the other side, there's a UV lamp irradiating, and then over time we can see the change in force, and therefore we can look at the viscosity, which is shown here. And what we can see here is that for monomer 3, again, we see a very steep increase in viscosity in the beginning, and then some kind of plateau which is reached. And for the other curves, the viscosity doesn't change in the same rate. And this might be an explanation for the conversion of the last slide, because also what we see is that the viscosity of monomer 3 is the highest of all monomers. So we can suspect that the molecule mobility is hindered there, which leads to an incomplete conversion. Something which you can also see is, of course, this curve, which looks quite ugly. And this is probably because either the rotor slipped from the polymer mixture, or the mixture slipped from the glass plate, and this is what results in this bluish curve. Then after polymerization, the polymer needs to be characterized. And here, as I said in the beginning, it's very important to look at the amount of this linear structure compared to this closed ring structure. In the NMR, we have this signal here, which corresponds to the double bond of the linear polymer. We have this signal, which can be assigned to all these CH2 groups next to any oxygen. So depending on which polymer we use, the amount will be different. And then we have this region here, and this is reported to be the protons of the cyclobutane structure. And by integrating and comparing the integrals there, we obtained the open ring structure percentage. And here we saw that with polymer 3, we got the biggest the highest amount of linear polymer, while all three, which show preorganization, have quite a huge amount of linear structure. And only the carbonate, which shows no preorganization, has a relatively high amount of closed ring structure. And this is actually also quite nice that we now see that the fastest polymer is also the one which shows less backbiting here. Also, the polymers were characterized in all other methods. So one is DSC, where we could look at the glass transition temperature, and we saw for monomer 3, it has the highest TG with 46 degrees, so above body temperature, but still below temperature you would need for a dental application, because there you come in contact with hot water or hot food, so something around 100 degrees C is needed there. Looking at the GPC curves, we see that monomer 3 has the lowest molecular weight, while monomer polymer, of course, polymer 1 shows the highest molecular weight. And this is the same trend as we can see for the TGA for the mass loss, where the monomer 3 is the least stable and polymer 3 is the stablest one. All these experiments should also be evaluated with a theoretical calculation. And here we looked at these 4 monomers, where we put them in a simulation box and used with vacuum, and as you can see here, the hundreds of molecules together to look at the interaction. The first interaction we looked at is the hydrogen bonding. And as the hypothesis was, we can see that for monomer 3, we see more or less twice the amount of hydrogen bonding compared to monomer 2 and 4. And the second one is the preorganization, and here we have either a value of 1, which shows a perfect alignment, or of 0, which shows a random alignment. And there are 2 trends which we can observe here. One is that all 4 molecules are more or less the same, so we don't see any difference, even though we see difference in hydrogen bonding, but the molecules itself are the same. And all values are around 0.25, so more or less a random alignment. And this can be explained because our preorganization site, if there is any, is not close to the reactive site, and we have quite a long chain which can still move around, so it's quite a flexible molecule nevertheless. So with this, I come to my conclusion. So I was able to show you that the synthesis characterization of 4 new monomers and polymers. Those showed very fast polymerization with a rate of up to 25% per minute. We got a very high overall conversion with maximum 97%. Also, the percentage of open ring structure was really nice and high with a maximum of 93%. And the theoretical calculations could support these experimental findings. So I can say that this is the first step of a successful design of new VCP-based dental matrices, because now with these findings we can design these bifunctional monomers which can form a network, and therefore we can go into dental application here. So I want to also mention, of course, the people important in this work beside me, which is, of course, my supervisor, Professor Agarwal, and also Professor Gekle and his PhD student, Ms. Plenareno, which were responsible for the theoretical calculations. Also, the group of Professor Senker, where I was able to measure solid state NMR. My group, of course, which is also helping, and not forgetting the financial partners, which is the university, the German Research Foundation, and the Volkswagen Stiftung. So thank you for your attention, and if there are any questions, feel free to ask.